Yesterday we were talking about Newton's second law problems that involve multiple masses. We call those system problems. Okay, we've gotten into a couple that involve pulleys and things like that. And all a pulley does in a system is redirect a force. Right? So it can make two vertical forces act against each other, as it did in the pulley question at the end of the day yesterday, and as it is doing in this question. Okay? The pulleys are simply making the two gravitational forces acting on the pails actually act in opposition to each other. Okay? So what I want you guys to try to remember from yesterday is the most important rule about the net force acting on the system. How much mass does the net force act on in the system? All of it. Okay? That's what we have to remember. Either we're dealing with individual masses in the system and the individual forces acting on them, or we're dealing with the system as a whole and all of the forces acting in it. Okay? So, having a look at this question here, we have a 20 kilogram truck tire that is lying on a horizontal frictionless table. Okay? The tire is attached to two light ropes that pass over light frictionless pulleys to hanging pails B and C. Pail B, which is the one on the left, has a mass of 8 kilograms. Okay? And pail C has a mass of 6.0 kilograms, and the tire is 20 kilograms. Calculate the acceleration of the system. All right? Give you a little bit of time on that. Something else to think about here is it's asking for the acceleration of the system. And acceleration is a vector quantity. However, the parts of the system are all moving in different directions. Think about what you might have to do there.
Plus minus.
No. Look at the key word. Can you actually give a direction for the acceleration of this system? No, because all the parts of the system go in different directions. All you can do is give the magnitude. You can calculate how fast the system is going to accelerate, but you cannot say a direction because pail C is going to move up, pail B is going to move down, and the tire is going to move to the left. Okay? We can't give a direction for the system because all the parts go different ways. Okay? Everyone follow me on that? It's one of those little tricks. It actually doesn't affect mathematically what you do. You still have to put pluses and minuses and all that in there. Okay? All right, give you a little bit of time on that one. Okay, first thing we have to do here is identify the forces that are acting in the system and calculate them. So we first have this force of gravity acting on the 6 kilogram pail. So that's m times g, so that's going to be 58.86 newtons. Okay, then we have this 8 kilogram bucket over here. Okay, it's going to have a force of gravity that's also m times g, 78.48. Okay. 0.48 newtons. All right, those are the only forces because they tell us the pulleys are frictionless, the table is frictionless. Those are the only two forces acting. Ben?
Should I use the negative?
Not for this one, no, because they're going to work against each other. While they're both down, when I set this up to calculate the acceleration of the system, I need to simplify my free body diagram. Okay, so this is why I'm not making, I mean, I could make them negative, but I'm going to change that in a minute. Okay, and this is why. How much mass is in this system? 34 kilograms. So remember, this is the thing we were talking about before. This has to move the entire system, all 34 kilograms. There are 58.86 newtons worth of force going one way, and there are 78.48 newtons going the other way. So now it isn't a matter of one being, or them both being negative. One is this way, and the other is opposite. Okay? Because I'm not going to be calculating or giving a direction here, I don't need to worry about them being both downwards. Okay, does that sort of make sense? Okay. So now that I have that, can I calculate the net force? Yeah, I'm going to use the vector sum of all forces. So F net will be 78.48 minus 58.86, or plus negative 58.86, which will give me 19.62 newtons. Okay, so that's my net force, 19.62 newtons. And that is pulling on how much mass? 34 kilograms. So can I calculate the acceleration of the system's magnitude, or sorry, the magnitude of the acceleration of the system?
Yeah.
Yes. All right, so that will mean 19.62 divided by 34 kilograms. Okay, so our acceleration, the magnitude of the system's acceleration is 0.58 meters per second squared. Now, if I were wording this question, I would word it this way instead. I would not ask for the magnitude of the system's acceleration. I would ask you for the acceleration of the tire. And that would make this question a little bit more difficult because it would cause people to do a couple of things. Some people would only use the mass of the tire when they do that calculation, because that's kind of what it implies. We have to remember, in the system, all parts accelerate at the same rate, so they all have to be included. Okay? And the other part is, now, since I named only one part of the system, can I put a vector on it?
Yes.
Yes, and I have to. What's the acceleration of the tire? I didn't say what's the magnitude of the tire's acceleration. What's the acceleration of the tire? 0.58 meters per second to the left. Okay? I have to indicate direction. Okay? So it's the little things, it's those little details, okay, that are important. Kind of like what I'm seeing on the map assignment here. Little details are important as they go through it, like remembering to do all of it. Spoiler alert, some of you didn't do all of it. Yeah, like a lot of people forgot to do the total trip. Yeah, a lot of people also forgot to put vectors on things, which is odd because the name of the assignment is vector activity. But little details, so important. Little details. Okay. All right. Let's skip over that one. Okay, this is another type of question for Newton's second law. It's what we call a static question. Okay, you're thinking like in English, static means unchanging. Okay, so in other words, if you have a static problem, it means the object's not doing what? Not moving. In any static situation, the object's not moving. What's the net force? Okay, that's something you have to keep in mind. Okay, for a static situation question, the object is not moving, and thus the net force is 0. That means all of the forces in the question, their vector sum is 0. Right, so that said, I want you to try this one. A store sign has a mass of 35 kilograms, and it's hanging from 2 different buildings. One cable is angled 55 degrees below the horizontal from one wall, and the second cable is horizontal and attached to a different wall. So it looks like this. Okay, this is one wall. This is the other wall. Okay, one cable is angled like this. So here's our sign. It's a mass of 55 kilograms. This cable is angled 55 degrees below the horizontal. The other cable is horizontal and is attached to that wall over there. Okay? You are trying to find the tension in this cable. That is, what is the pulling force being exerted by that cable? Keeping in mind that all the forces in this question add up to 0. Okay. So, there are how many forces in this question? 3. Okay, there are 2 cables and gravity. All right, take it from there. I'll add something else in a minute or two here, but I want to see if anybody can get it right now. Okay, so let's add on a couple of forces here. Okay, we need the force of gravity on this diagram. Okay, essentially I'm turning this into a free body diagram. So we got 55 kilograms being pulled by gravity. So 55 times 9.81. Sorry, 35. 35 times 9.81. Okay, 343.35. 35, 343.35. 35 newtons. Okay. the sign's not moving. And cable 2 is horizontal. So can cable 2 support any of that 343 if it's straight down? No, they're perpendicular. Okay? Cable 2 is not supporting any weight. What's cable 2 doing? It is, yeah, it's stabilizing. It's offsetting something about the first cable, because the first cable's angled. It's pulling both vertically and horizontally, which means it has a horizontal component and a vertical component. How big is its vertical component? 343.35. It has to be. If the net force in this question is 0, if the sign's not moving, there's got to be exactly the same amount of newtons up as there are newtons down. Okay, so that means this side is 343.35 newtons. Can I figure out what the tension in cable 2 is now?
Yeah.
Okay, I'll give you a couple minutes, see if you get it. All right, so the rest of this goes like this. If I know this side and an angle, can I find out the other two sides of the triangle? Okay, which side of the triangle do I need to find? Right, I need to find the adjacent side, because it's how much cable 1 is pulling to the left. The only thing cable 2 is doing is offsetting that force. That's why the sign isn't moving up or down, or right or left, because all the forces add up to 0. Okay? So if I can find out what this side is, that will be the tension pulling to the right in cable 2. Does everyone follow my logic on that? Okay. So is there a whole lot of math in this question? No. I had to calculate the weight of the sign. I'm going to have to do a trig calculation to get this number, and I'm done. Most of this question is intuitive. Okay? And that's going to be the way it goes for most of our Newton's second law questions. So I have the opposite side, I'm looking for the adjacent side, and I have the angle. Okay, so I've got the tan of 55 equals 343.35, the opposite side, divided by the adjacent side, so I'm looking for that. So I'm going to go the adjacent side equals 343.35 divided by the tan of 55. Okay, that will give me the tension in cable 2. Oh, not inverse. Stupid. Yeah, you're right. 343.35 divided by the 10 of 55. Okay, 240 newtons is the tension in that cable. Okay? So again, I know I've said this like 100 times, I'll say it another 1,000 times probably before the unit's over. It's really important to visualize the situations that we encounter, okay, in Newton's second law problems. Okay. Anybody need that one anymore? Okay, I want you to try this one. Pulleys. Okay, we've done a couple of pulley ones now. So I have a 4 kilogram mass sitting on a frictionless surface. Okay, so this surface here is frictionless. It's over a frictionless pulley with a massless rope, okay, attached to a 5 kilogram mass. I want you to calculate the acceleration of the 5 kilogram mass. Okay, give me a couple minutes on that one. Okay, so since I screwed this up, and I said the table's frictionless, even though I wrote the first thing on the board was friction on the table, 32 newtons, okay? So there's friction on the table, 32 newtons, this way, okay? Because that friction acts directly on the 4 kilogram mass. What's acting on the 5 kilogram mass? Gravity. Gravity, okay, so that's going to be 49.05 newtons. And that's the force of gravity. Okay, those are the only two forces in the system. The two masses are attached by a rope, so I can simplify this to look like this. There's 9 kilograms worth of mass being pulled this way by 49.05 newtons worth of force, gravity, and resisted by 32 newtons worth of force, friction, this way. All right, so when I do this, I should have 17.05 newtons worth of net force, right?
Yeah.
Okay, so F net equals 17.05 newtons. All right. Now, the question wants to know the acceleration of the 5 kilogram mass. How do I get that? Divide this by 9 kilograms. Remember I told you that was one of the tricks I might try. Okay, I asked for part of the system, even though you'd have to use the whole system to get its answer. Okay, the 5 and the 4 are both being moved by this net force. Okay, so when I calculate the acceleration of the system, that will be 17.05 divided by 9 kilograms, the mass of the entire system. Okay, so 17.05 divided by 9. There's the acceleration of both parts. But here's what I have to do now. It asked about the 5 kilogram mass. So I'm going to say 1.9 meters per second down. Right? 5 kilogram mass is going to move down. It's hung over the pulley. Right? In fact, I only have one significant figure here, so it should actually be 2 meters per second squared down. Okay. Okay. I did one like this yesterday.
Yeah. I remember.
Okay. Well, you're going to try it again.
Yay.
But we did one just like this, so if you look back in your notes, you might see it. You know, so you did it this is supposed to. Okay. Yeah. If I want to find the acceleration of the 40 kilogram block, I need to find the acceleration of the entire system, which means I'm going to simplify this mess down to this. That's weird. Put it in the wrong place. Okay, so I have 100 kilograms worth of mass here, right? 60 plus 40. All 100 kilograms is being pulled this way by 150 newtons and this way by 120 newtons. My net force is 30 newtons in a forward direction. Acceleration is F net divided by m. 30 divided by 100 is 0.3 meters per second squared forward. Okay, that's all I have to do to get the acceleration of either block. Now that I have that, now I can work towards finding the tension in B, because I need to have the acceleration of each piece, because I'm going to have to separate the pieces to find the tension in cable B, just like I did the other day. So my suggestion would be to use the 40 kilogram block to find the tension in B, because the tension in B is pulling on the 40 kilogram block, along with the other 2 forces you were given. Okay, so I would suggest your next step is to draw a free body diagram for the 40 kilogram block and see if you can find the force pulling back on it as a result of the rope. Okay? Okay, so the second part of this is calculating the tension in the cable that's connecting the 2 blocks. All right, so as I said, the easier way to do that is to just use the front block, because it involves one less mathematical operation. It's just a subtraction operation, but it's one less thing. Okay, so I'm going to draw the 40 kilogram block. Okay, it's being pulled this way by 150 newtons. It tells us that the force of friction acting on it is 48 newtons, and cable B is the other force that is pulling back on the 40 kilogram block. Now, I also know that the acceleration of this block is 0.30 meters per second squared. Since I know its acceleration and its mass, what can I find? F net. Yeah, I can find the net force acting on just the 40 kilogram block. All right? The reason that that's important is because I'm going to need the net force if I'm going to find the force I'm missing. Because I know that this force, negative 48, plus 150, plus the force of B, I know that those 3 things will add up to whatever I get for the net force, right? Because net force can be calculated by m times A, or the vector sum of all forces. So I'm going to find what m times A is, so 40 times 0.3. Okay, so 12. Okay, so we've got 12 newtons is my net force, 12 newtons forwards. Okay, and that's going to equal negative 48 newtons plus 150 newtons plus the force in B. So I'm just going to isolate the force in B by subtracting the other two over, okay, or adding actually the 48. Okay, so I'm going to have 12 minus negative 48 minus 150 equals the force in B, which will give me a negative number, which is good because from the 40 kilogram block's point of view, that force is backwards, yeah, negative. Okay, so we're going to have 12 minus negative 48 minus 150. All right, so there's the force in the cable, 90 newtons backwards. Okay. Everybody follow on that? All right, so again, was there any like rocket science type math in this? None. There really weren't even any vectors other than positive and negative, okay, to deal with. But there's a lot of, I've got to visualize, I've got to understand what's happening, what's pulling on this box, what's pushing on this box, okay, all of that kind of stuff. It all comes into play, okay, and there's a lot to think about and visualize. Okay. Situation like the others, like the sign question we had. This is another static question. Okay? The 120 kilogram mass is not moving. So if you've ever been to like a Stampeders game, you know they got the big speaker hanging in the middle. Okay? That's what this is. Big speaker hanging in the middle. Okay? Like the big score clock hanging in the middle. Okay? So it's suspended by two cables. Those cables are 100 degrees apart. And the mass of the clock or speaker is 120 kilograms. I want you to find the tension in these cables. There's a hint. They're equal. Okay. The tension in the cables is equal because they're splitting it equally. Okay, so look in here, guys. The forces acting. Okay, the forces acting in this are that we have 120 kilograms hanging, which means there's a force of gravity acting on that 120 kilograms. So 120 times 9.81, okay, gives us 1177.2 newtons. Okay, then we have two cables that are splitting the difference on the force of gravity. Each one of them is pulling up and to the opposite side. So how much of this 1172 newtons is this side of each cable's triangle? Okay, you're right. I wasn't thinking the degrees. You're right. Each one of these is a 50-degree angle. How much of this force is each cable holding? Half. Okay? The vertical component for each cable is half this number. You can't use the whole number for one cable. If you do that, there's twice this number pulling up. What's the clock doing? Flying upwards into the air. Okay? At 9.81 meters per second squared, by the way. Okay? That's not what it's doing. Okay? It's just hanging there. So I have to take, for each one of these cables triangles, only half of this number. So I'm going to divide that by 2. Okay? There's my vertical component for each cable, 588.6 newtons. So again, I think a lot of people probably got close, but they probably used 1100 instead of the 588. Just those, again, I'm just pointing out those little details here. Okay, I know right now it kind of probably feels like I'm beating you down. Okay, and I'm not trying to do that. I'm just showing you how much there is to think about. Because there's trig in there, I'm not sure if that'll work, so we'll just see in a second here. Probably, but I don't want to say for sure. Okay, so we've got our 50-degree angle here, and we've got our vertical component. We're looking for the hypotenuse of this triangle, so we're going to use cos, okay, and we're going to say that the cos of 50 degrees equals 588.6 divided by the hypotenuse of the triangle, which is what we're looking for. So to get the tension, which is the hypotenuse, we'll have 588.6 divided by the cos of 50. All right, so each cable is bearing or is exerting 9.2 times 10 to the 2 newtons worth of force. Okay? Actually, sorry, we have 3 significant digits here, so we could say 916 newtons worth of force at 50 degrees from vertical. Everyone okay on that one? Well, when I divide the 100 by 2, it should be 50.0. Okay, any other questions on that one? No, so that was a little bit tricky. Okay. Now, we haven't started talking about inclined planes yet. I want to save inclined planes till tomorrow because inclined planes are my favorite kind of Newton's second law problem. Because I'm that nerdy, I actually have a favorite kind of Newton's second law problem. Hey, you have to be comfortable in your own skin. I know, I'm nerdy. Nerdy's code for genius. My son never said that's awesome. Okay, so we're going to go over inclined planes tomorrow, but let's just talk quickly about the principle behind an inclined plane. Okay? You need to understand the principle behind an inclined plane, or you will be an inclined plane wrapped around an axis. Oh, an inclined plane wrapped around an axis. A screw. You'll be screwed. Okay, that's a Sheldon Cooper joke. Okay, but okay, that's why a screw works the way it does. Okay, it's basically allowing you to turn something into like a screw into the piece of wood because it's an inclined plane. It's easier than just pushing it in. Okay, the inclined plane helps. So, what does an inclined plane do? An inclined plane is what we call a force multiplier. Okay, it allows me to do the same amount of work with less force, or using less force. Okay? If I was to push this block up the ramp to the top, I wouldn't have to use as much force as if I lifted it directly there from the floor. Okay? If I lift it directly from the floor, I have to work directly against gravity, and that's a lot more work than if I set it on the ramp. Because what will the ramp do? Yeah, it'll support some of the weight. It'll push back. All I have to do is push it up the ramp. If the ramp's frictionless, that'll be really easy. There's a little bit of friction on the ramp. It'll still be easier than lifting it by myself. Okay, guys, this is how the Egyptians built the pyramids. They didn't have help from aliens. They had sand and slaves, and they had lots of both. They could make really long ramps and have lots of people pull rocks, okay, up these really, really long ramps. Okay, so it works. Okay, they're a force multiplier, and that's what we're going to look at tomorrow. Is how does an inclined plane help us? Okay, and how does it work? So the forces involved in an inclined plane are gravity. Which way does gravity pull? Down. Straight down. That's the thing we have to remember. Okay, gravity pulls straight down on any object placed on an inclined plane. But the inclined plane pushes back, but it doesn't push straight against it. It pushes straight out. So the force of the inclined plane, which we call the normal force, pushes that way. If I take those two things added together, tail to head as vectors, I get my net force, which we call F parallel, because it's parallel to the plane. That's why an object on an incline moves either up or down the incline. Okay? Because the net force is either up or down the incline. Now, in this case, the net force would be which way? Down the incline. What if I'm pushing up the incline? No, then the net force will be up the incline because I would add on to this my upward force, which would be back up the incline. Okay? Yeah, weird, but it's there. Okay, so we'll be talking about inclined planes tomorrow. Okay, the big thing with inclined planes is when we draw this triangle in here, this angle is always the same as this one. Okay, it's because these two forces are related by the angle of the ramp. They have to have the angle of the ramp in between. But that'll just tell me length. It's not. This is like a ramp. Right? It won't tell me forces. It'll just tell me how long it is. Okay. Now I want to quickly talk about your math assignment.